Hello everyone again and welcome to my channel. In here we're going to be focusing on the applications of motion of a charged particle, and this is actually crucial in terms of looking at the relationship between the electrical field and the magnetic field, and we talked about those on our previous videos, and we're also going to see how we'll be able to combine both together to see how we can be able to introduce some fantastic applications in modern physics. Now, one of these is the use of a velocity selector and how this particular instrument is actually crucial in terms of we being able to detect various compounds that are actually charged. So in here we have a skeletal diagram of this particular instrument, and in here we just have an interesting look at this particular instrument where we have a gun in here that shoots a particle or a charged particle, and in here we do have two rods in here, and we're going to see how we'll be able to position three elements in here that are really important for this instrument to actually function properly. Now, first instrument part that we need to label is the two rods, which are the positive and the negative side. So it doesn't matter where you position it as long as you can pick one side versus the other. That is really important in here. So we have a positive rod which goes all the way down here, and in here we have a negative rod which goes all the way down here or up here. Now, why am I putting the rods here and why am I leaving it positive and negative? Why I'm doing that is because I'm trying to introduce an electrical field in that particular chamber channel over here where our charged particle, which is actually this particle here, which is positive and moving at a specific velocity, is going to be passing through. So once I introduce that, I know that my electrical field is going to the left. So once I'm able to dictate that, then I'm good in there because I'm always going from positive to negative over there. This is actually my electrical field over there. Now, on the other side, how am I going to label my second component? My second component is actually going around the chamber, which is the magnetic field. So the magnetic field is around this particular channel chamber, and it's actually pointing into this particular page, which is represented as X in here. So once I'm able to introduce that, then I know that this is my magnetic field, and by that way I can be able to combine both properties into this particular chamber and subject my third property, which is a positive quantity of charge that will actually go in through this particular channel. Now, one important thing we need to note in this particular particle is that there are three properties also that are actually important for the success of this particle and for the detection of this particle. One of it is the mass of the particle. Secondly, we have the quantity of charge that the particle contains, either positive or negative. And last and foremost, we need to take into account the velocity that that particular charged particle is moving at, going from top to bottom, which is where our detector is actually positioned at. Now, once we're able to take into consideration all these properties in here and also the electrical field and magnetic field in here, then we need to take into account what do we need this particular particle to actually do. We want it to hit the detector, right? So it must go in a straight line, which is in that particular manner. For it to go through a particular straight line pattern, this particular charged particle must not deflect, because if it deflects, it will hit or lean towards the left or lean towards the right with respect to our particular rod system and also with respect to the magnetic field. So what are the two things that we need to take into account in here? We need to take into account that the force must be equal to 0, which is the net force. Now, our net force must be equal to 0. And what are the two forces that are actually introduced in here? We need the electrical field force, which is actually represented as E, F, and we need to take into account the magnetic field force, which is represented as FB. So, in terms of the direction of our electrical field force, it's going to the left. So since it's leaning towards the left, then we expect it to be negative by default, because by choosing our signs we want our right in here to become positive and our left to be negative force in here. So since force is a vector, then our electrical force field will actually point towards the left with the negative charge on it, while in terms of the magnetic field, we can determine that using our magnetic field right hand rule, where we want our right hand in such a way that this is our force, this is our velocity, and this is our magnetic field. By that way, if I want my magnetic field to be into the page over here, and we want our velocity to actually point down, the best way to actually position our force is actually leaning towards the right, because if by using your right hand, you can actually see that this thumb actually goes with our magnetic field, and this particular finger here points in the direction of the velocity of our particle. So our magnetic force field will actually point to the right, which is positive. So where our net force is equal to 0, then our formula is QVB for our magnetic field. You add it with negative quantity of charge multiplied by our electrical field, and this here will be equal to 0. So once this is equal to 0, then we solve for our velocity. What we realize is that our velocity is dependent on the electrical field and our magnetic field. So this must be taken into account the fact that our velocity of our charged particle must be at constant speed, and it must actually move in a straight line without any form of deflection in order for it to hit our detector over here. So that's about it for this particular video. I hope you're able to understand how the velocity selector works, and see you all on my next video. Have a good day. Peace, love you all, and be smart. Bye.